NASA just rewrote the numbers. Not in a press conference. Not in a peer-reviewed paper. Quietly on a government website. Within 48 hours of a Harvard professor pointing out an impossible coincidence, the Jet Propulsion Laboratory changed their acceleration model for 3I Atlas by a factor of 6. They switched from water ice physics to carbon dioxide physics overnight. And here's what nobody is talking about. The old model showed 3. Atlas arriving exactly at Jupiter's gravitational doorstep. The new model pushes it just outside. Coincidence or correction? Tonight we're going to examine every piece of evidence. The revised trajectory data, the missing mass paradox, the X-shaped jets that should not exist, and the radio signal that appeared at the exact frequency where scientists have been listening for extraterrestrial communication since 1977. By the time you finish this video, you will understand why the United Nations has activated a planetary defense drill around this object and why December 19th might be the most important date in astronomical history. Before we begin, if you find value in these deep investigations, take a moment to like this video and subscribe. Let's begin. The revised model controversy. NASA quietly rewrites the numbers. Something extraordinary happened in the final days of November 2025. Something that would have gone completely unnoticed if it were not for the obsessive attention of independent researchers watching every update to NASA. Jet Propulsion Laboratory Horizon S database, the numbers changed, not by a small margin, not within the expected uncertainties. The primary non-gravitational acceleration parameter, the value scientists use to calculate how much 3I Atlas deviates from a purely gravitational trajectory, dropped by a factor of 6, from approximately 1.6. 6 asterisk 10⁻6 astronomical units per day squared, down to 6.8 asterisk 108. Think about that for a moment. This is not a minor adjustment. This is a fundamental revision of how we understand this object's movement through our solar system. The timing makes this revision even more remarkable. Just days earlier, Avi Liu at Harvard had published a detailed analysis showing something that caught the attention of researchers worldwide. The original JPL data predicted that 3-2 Atlas would arrive at Jupiter on March 16, 2026, at a distance that matched almost perfectly Jupiter's Hill radius. The Hill radius is the boundary of Jupiter's gravitational influence, the invisible sphere within which the giant planet's gravity dominates over the Sun's gravitational pull. Objects arriving at exactly this distance could theoretically be captured into orbit. They could release smaller objects that would remain bound to Jupiter. It is precisely where you would position a spacecraft if you wanted to deliver something to the Jupiter system. The statistical probability of this coincidence occurring by chance. Now, here is where the story takes its turn. Lowe sent an email to David Diania, the navigation engineer at JPL, responsible for maintaining the 3 Atlas trajectory data. He shared his analysis of this remarkable coincidence. There was no response to that email, but within a couple of days, the model changed. The new model uses what scientists call an inverse square dependence on distance from the Sun. This pattern, written mathematically as 1, R2, describes how carbon dioxide ice sublimates as a comet approaches the Sun. The previous model used a steeper dependence appropriate for water ice sublimation, based on decades of work by Brian Marsden and his collaborators. Water ice and carbon dioxide ice behave very differently. They sublimate at different temperatures, at different rates, and they produce different acceleration profiles as a comet moves through the inner solar system. So which model is correct? The James Webb Space Telescope observations from August 2025 give us our first clue. Those observations, led by Martin Cordner and his team, revealed something extraordinary about 3I Atlas. The coma surrounding this interstellar visitor is dominated by carbon dioxide. The ratio of carbon dioxide to water in the outgassing is 7.6 to 1 plus or minus 0.3. That is among the highest ever observed in any comet anywhere. It is 4.5 standard deviations above the trend line for long period in Jupiter family comets at similar distances from the Sun. So at first glance, switching to a carbon dioxide model seems scientifically justified. 3 Atlas is rich in carbon dioxide. Carbon dioxide drives its activity. Case closed. But the story is not that simple. The luminosity evolution of 3I Atlas tells a different story. observations from Stereo and GOES 19 during September and October 2025 showed 3I Atlas brightening at an extraordinary rate as it approached perihelion. The brightness increased inversely with distance to the power of -7.5, not -2, as the new JPL model assumes. 7.5. That is dramatically steeper than what you would expect from simple carbon dioxide sublimation following an inverse square law. This steep brightening profile suggests that something unusual was happening near perihelion. The object was not simply warming up and releasing gas at a steady, predictable rate. It was doing something more, something the new model does not capture. When you apply this steeper radial dependence to the trajectory calculations, something interesting happens. The predicted closest approach to Jupiter shifts back toward agreement with the Hill radius value. The coincidence returns. Let me be clear about what we are dealing with here. The question is not whether NASA made an error. Trajectory refinement is normal science. As new data comes in, models get updated. That is how the process works. The question is whether the new model accurately captures the physics of what 3I Atlas is actually doing. And on that question, the data sends mixed signals. The luminosity curve says the non-gravitational acceleration near perihelion was steeper than the new model assumes. The composition data says carbon dioxide is the dominant volatile. The trajectory shift says the object is now predicted to pass just outside Jupiter's Hill radius, rather than exactly at it. And the timing of the model change, immediately after a prominent scientist pointed out an uncomfortable coincidence, raises questions that pure mathematics cannot answer. Here is what we know with certainty. The non-gravitational acceleration is real. The detection now stands at 10 standard deviations of statistical significance. That is about as solid as astronomical measurements get. 3 Atlas is not following a purely gravitational path. Something is pushing it. The question that haunts every researcher studying this object is simple. What is doing the pushing? For a natural comet, the answer should be straightforward. Gas escapes from the surface as ices sublimate in sunlight. The gas carries momentum away from the nucleus. By Newton's third law, the nucleus gets pushed in the opposite direction. We have seen this happen with countless comets. It is well understood physics. But 3 Atlas is not behaving like countless comets. The acceleration measured near perihelion requires, by the laws of momentum conservation, that 3 Atlas lost at least 10 to 15% of its mass in a matter of weeks. For an object with a minimum mass of 33 billion tons, that means billions of tons of material should have been ejected into space. That material should be visible. It should form a massive cloud of gas and dust surrounding the nucleus, trailing behind it, pushed by solar radiation pressure, into a classic cometary tale. The images from early November tell a different story. When 3 Atlas emerged from behind the sun after perihelion, observers around the world trained their telescopes on the returning visitor. The Virtual Telescope Project captured it on November 5th. The ICQ Comet Observations Group photographed it on November 8th. Amateur astronomers with modest equipment produced image after image, and there was no clear cometary tail. Let that sink in. An object that should have lost billions of tons of mass showed no obvious tail pointing away from the sun. Instead, what the images revealed was something far stranger, a complex network of jets. Some pointing toward the sun, some pointing away, some pointing sideways. At least 7 distinct features extending hundreds of thousands of kilometers in multiple directions. This is not what comets do. Rather, this is not what any comet we have ever studied has done. The comparison to Comet Lemon, photographed by the same observers just days later, makes the contrast stark. Lemon shows exactly what you would expect, a clear tail streaming away from the sun, pushed by radiation pressure, behaving precisely as cometary physics predicts. 3 Atlas shows something else entirely. Now, I want to be careful here. I'm not making claims I cannot support. There are natural explanations for unusual jet structures. Comets are complex objects with varied surface compositions. Pockets of different ices can sublimate at different rates. The rotation of the nucleus can create complex outgassing patterns. We have seen jets from solar system comets before. But there is something about the geometry of the 3 Atlas jets that does not fit the standard picture. Something about their orientation, their collimation, their relationship to the object, is known rotation period that points toward a mystery we have not yet solved. And that mystery connects directly to the model revision we started with. Because if the jets are not simply sublimating ice being pushed by sunlight, if there is some other mechanism at work, then the carbon dioxide model might be missing something fundamental about what 3I Atlas actually is. The revised trajectory now predicts a closest approach to Jupiter of 53.587 million kilometers plus or minus 45,000 kilometers. That puts 3I Atlas just outside the Hill radius. It's just beyond the boundary of gravitational capture, just far enough away that any objects released near perihelion would not remain bound to Jupiter. But here's the thing about orbital mechanics. These predictions depend on the model. Change the model, change the prediction. And the luminosity data suggests the model might need changing again. We're in the strange position of watching science happen in real time on public databases, with researchers around the world checking each other's work and questioning each other's assumptions. The truth about 3I Atlas is not being decided in secret meetings or classified briefings. It is being worked out in the open. One observation at a time, one model revision at a time. What happens next depends on the data that comes in over the following weeks. The International Asteroid Warning Network campaign is now active, with observatories around the world contributing measurements. The Hubble and Webb telescopes will observe 3 Atlas again near its closest approach to Earth on December 19th, and every observation will either confirm the current model or force another revision. The coincidence with Jupiter's Hill radius might be exactly that, a coincidence. A quirk of orbital dynamics that means nothing beyond the mathematics. Or it might be the first hint of something we're not ready to accept, something that would rewrite our understanding of what visits us from the darkness between the stars. The jets streaming from 3 Atlas hold more secrets than any model can capture, and those secrets are about to get much stranger. The Jupiter, coincidence, Hill radius, and the question of intent. Let us talk about Jupiter, the largest planet in our solar system. A world so massive it could swallow 1,300 Earths and still have room for more. A world whose gravity reaches out across hundreds of millions of kilometers, shaping the orbits of asteroids, capturing passing comets, and creating a zone of influence that astronomers call the Hill sphere. The Hill radius of Jupiter extends approximately 53 million kilometers from the planet's center. Inside this boundary, Jupiter's gravity dominates. Objects moving slowly enough can be captured, pulled into orbit, made permanent residents of the Jovian system. The 4 Galilean moons orbit well within this sphere. So do dozens of smaller moons. So do the temporary captures, the comets and asteroids that Jupiter occasionally snags from passing trajectories. Now here is what makes the 3 Atlas trajectory so remarkable. When you trace its path forward from perihelion, accounting for the non-gravitational acceleration measured near the Sun, the object arrives at Jupiter on March 16, 2026. And the distance of closest approach before the recent model revision matched the Hill radius to within the measurement uncertainty. Not somewhere inside the Hill sphere, not somewhere outside. Right at the edge, right at the boundary between capture and escape. Right at the precise distance where an object could release smaller components that would remain gravitationally bound to Jupiter without the parent body itself being captured. Steve Fairfax first brought this coincidence to Avi's attention. Fairfax had been running the numbers, checking the JPL trajectory data, and noticed something that should not have been there. The minimum distance from Jupiter, labeled min in the technical notation, came out to 53.08 million kilometers, plus or minus 60,000 kilometers. Jupiter's Hill radius at that orbital position, 53.1 million kilometers. The numbers matched. Think about what this means from a probability standpoint. Jupiter's Hill radius represents a thin shell in space, a boundary zone perhaps a few hundred, 0 kilometers thick, where the gravitational transition occurs. The volume of space within Jupiter's orbit around the Sun is enormous, roughly 100 trillion kilometers, if you consider just the region interior to Jupiter's orbital path. The probability of a random interstellar object arriving at exactly the Hill radius distance by pure chance is vanishingly small. Low calculated the odds at less than 4 in 100,000. Other researchers have come up with similar figures. This is not the kind of coincidence that happens often. This is not the kind of coincidence that should be dismissed without investigation. But wait, there is more context to consider. 3I Atlas did not take a direct path to Jupiter. It came screaming in from interstellar space at a speed of over 250,000 km/h. It passed Mars at a distance of 29 million kilometers on October 3rd. It swung around the Sun at perihelion on October 29th, coming within 203 million km of our star. It experienced measurable non-gravitational acceleration during this close solar passage, and now it is heading outward toward a rendezvous with Jupiter in March. Here's where the physics gets interesting. The non-gravitational acceleration occurred near perihelion. This is exactly when you would expect a comet to experience maximum outgassing, as solar heating peaks and ices sublimate at their fastest rate. But it is also, as rocket scientists well know, the optimal point for any trajectory modification. The OTH effect, named after the pioneering rocket theorist Hermann Oberth, describes how a spacecraft can gain or lose energy most efficiently when it's moving fastest. At perihelion 3I Atlas was traveling at approximately 68 kilometers per second relative to the Sun. Any thrust applied at this point, whether from outgassing or from something else, has maximum impact on the final trajectory. If you wanted to fine-tune an approach to Jupiter, perihelion would be exactly when you would do it. The measured non-gravitational acceleration amounted to a tiny nudge, about 0.02 millimeters s². That sounds insignificant until you consider how long it acts and how it compounds over time. Applied over weeks near perihelion, this small acceleration shifts the trajectory by just enough to change the Jupiter encounter distance by about 100,000 km, just enough to bring it to the Hill radius. Now, I need to be careful here. I am describing a pattern in the data, not making a claim about intent. The natural explanation is that 3I Atlas is a comet doing what comets do. Outgassing occurs, momentum is transferred, the trajectory shifts by whatever amount the physics dictates. The match with Jupiter's Hill radius would then be a coincidence, improbable, but not impossible. The alternative explanation is that 3E Atlas is not purely natural, that the trajectory was adjusted deliberately, that the perihelion passage was used to fine-tune an approach to Jupiter's gravitational doorstep for purposes we can only speculate about. Both explanations fit the current data. That is the frustrating reality of where we stand. What would it mean if the coincidence is real? If 3IE Atlas was designed to arrive at Jupiter's Hill radius, consider the geometry. An object passing at exactly the Hill radius could release smaller components, probes if you will, that would have just enough velocity to enter Jupiter's gravitational influence. These smaller objects could spiral inward, eventually establishing orbits around Jupiter or its moons. They could monitor, they could collect data, they could wait. Jupiter has been visible from the Milky Way galaxy for 4.5 billion years. Any civilization with sufficient astronomical capability anywhere in our galaxy could have spotted it, could have calculated its mass, could have recognized it as the dominant gravitational presence in this planetary system. If you were going to send something to investigate a solar system from afar, Jupiter would be a logical target. It is big. It is bright. It has a rich system of moons that might harbor conditions for life. And it sits in the outer solar system, far enough from the central star to provide a quiet vantage point for observation. I am speculating now, but speculation grounded in physics and logic. The model revision we discussed in the previous chapter shifted the predicted closest approach distance. The new calculation puts 3I Atlas at 53.587 million kilometers from Jupiter, plus or minus 45,000 kilometers. That is about 500,000 kilometers outside the Hill radius. Close, but not matching. Does this revision settle the question? Not necessarily. The new model uses an inverse square dependence on solar distance for the non-gravitational acceleration. But as we discussed, the luminosity data suggests a much steeper dependence near perihelion, something closer to the 7.5 power observed by Ken Jeong and K.L. Badams. If the actual acceleration profile was steeper than the model assumes, the trajectory prediction would shift. The Hill radius match could return. You're dealing with a moving target. As more observations come in, the models will be refined, the predictions will shift, and the question of whether 3 Atlas is aimed precisely at Jupiter's gravitational boundary will remain open until we have much more data. There is another aspect of this Jupiter encounter that deserves attention. NASA's Juno spacecraft is currently orbiting Jupiter. It has been there since 2016, studying the giant planet's atmosphere, magnetic field, and interior structure. When 3 Atlas makes its closest approach in March 2026, Juno will be approximately 53 million kilometers away from the interstellar visitor. That is close enough for detection. Maybe Juno carries a radio instrument that operates at frequencies from 50 Hz to 40 MHz. If 3 Atlas emits any radio signals in this range, Juno might pick them up. The spacecraft was not designed for this purpose, but science often advances through opportunistic observations. Sometimes you detect things you are not looking for. ESA's JUICE spacecraft, currently en route to Jupiter, will also be in the vicinity. JUICE is farther from 3 Atlas than the Mars orbiters were during the October encounter. But it is observing the object in a more active state post-perihelion, when outgassing and jet activity are at elevated levels. The data from JUICE observations is not expected until February 2026 due to bandwidth limitations on the spacecraft's communication systems. So we wait. We observe, we refine our models. We keep asking the question that nobody can yet answer: is the Jupiter coincidence meaningful? The skeptical position is clear and defensible. Random events sometimes produce unlikely outcomes. We notice the hits and forget the misses. If 3 Atlas had arrived at some unremarkable distance from Jupiter, nobody would be writing about it. The fact that it happens to match the hill radius might be nothing more than the kind of pattern our brains are wired to find, whether it exists or not. The alternative position is equally clear, though more controversial. The trajectory of 3 Atlas shows multiple improbable features: the ecliptic alignment, the close approaches to Mars, Venus, and Jupiter, the solar conjunction that hit it from Earth at perihelion, it's a non-gravitational acceleration that shifted its path by just the right amount. When improbabilities stack up, at some point you have to ask whether chance is really the best explanation. Neither position can be proven with current data. That is the honest scientific assessment. What we can do is identify the observations that would distinguish between these possibilities. If 3 Atlas releases smaller objects as it passes, Jupiter objects that enter the Hill sphere and establish orbits that would be strong evidence against the natural hypothesis. If the jets and outgassing behave exactly as cometary physics predicts, with no anomalies, beyond what strange composition might explain, that would support the natural interpretation. The next few months will be decisive. The ION campaign runs through January 2026. The December 19th close approach to Earth will provide the best observation opportunities we will ever have. And the March Jupiter encounter will either vindicate the skeptics or force a profound reassessment of what we think we know about visitors from interstellar space. In the meantime, the jets from 3 Atlas continue to confound expectations. 7 distinct features pointing in directions that should not be possible for a rotating nucleus with standard cometry physics. The explanation for these jets might hold the key to everything else, because if the jets are not what they appear to be, then neither is 3 Atlas. 7 jets, 1 mystery. The complex structure that defies rotation. On the morning of November 8, 2025, at 4:10 Universal Time, 3 astronomers in Europe captured something unprecedented. Michael Jagger, Gerald Riemann, and Enrico Prosperi trained their telescopes on the patch of sky where 3A Atlas had emerged from solar conjunction. Stacking 24 exposures in the green filter, each lasting 35 seconds, plus additional exposures in red and blue, what they recorded changed the conversation about this interstellar visitor. The images showed a glowing halo extending outward to nearly 500,000 km from the nucleus. That alone was remarkable. It was not the halo that caught everyone's attention. It was the jets. At least 7 distinct features, some pointing toward the sun, some pointing away, some pointing in directions that had no obvious relationship to solar illumination at all. This was not supposed to happen. To understand why these jets are so strange, you need to understand how comets work. When a comet approaches the sun, solar radiation heats its surface. Ice is embedded in the nucleus. Water ice, carbon dioxide ice, carbon monoxide ice begin to sublimate. Transitioning directly from solid to gas, this gas escapes the surface at thermal velocities, typically around 300 to 400 meters per second for the temperatures involved. As the gas escapes, it carries dust particles with it, creating the fuzzy glow we call the coma. The escaping gas also pushes back on the nucleus, Newton's third law in action. For every molecule that flies off in one direction, the nucleus gets a tiny shove in the opposite direction, Add up billions of molecules escaping every second, and you get a measurable force. This is the non-gravitational acceleration that astronomers track. Now, here is the key point. Ice sublimates when it is heated. The sun heats the surface. Therefore, the most intense outgassing should occur on the sunward side of the nucleus where solar illumination is strongest. The resulting jets should point generally toward the sun, or at angles consistent with the geometry of solar heating. When you look at familiar comets, this is exactly what you see. Sunward jets, tails pushed away from the sun by radiation pressure. A clear geometric relationship between the sun's position and the features emanating from the nucleus. 3 Atlas shows something different. The November 8th images revealed jets pointing in multiple directions, including away from the sun. The November 9th images captured by Frank Nebling and Michael Bachner showed even more dramatic structure. 2 anti-tailed jets extending toward the sun out to nearly 1,000,000 km. A longer, tightly columnated jet extending away from the sun out to almost 3,000,000 kilometers. The angular extent of these features? About 30 arc minutes for the longest jet equals the apparent diameter of the full moon. These are not subtle features. These are enormous structures spanning millions of kilometers of space, and they should not exist, at least not in the form we observe them. Here is why. 3I Atlas rotates. Back in July and August of 2025, before it disappeared behind the sun, researchers analyzed its brightness variations and determined a rotation period of 16.16 hours, plus or minus about 30 seconds. This is a typical rotation period for a cometary nucleus. Nothing unusual there. But think about what rotation means for jet formation. If a jet emerges from a particular spot on the surface, that spot rotates with the nucleus. Over 16 hours, it completes one full rotation. A jet that forms when the spot faces the sun will shut off when the spot rotates to face away. The resulting pattern in space should show evidence of this periodic behavior. At a gas velocity of 400 meters per second, material travels about 23,000 kilometers during one rotation period. A jet that fires intermittently, turning on when the surface is illuminated and off when it is not, should show gaps. It should look like a series of puffs, what one researcher described as PS in a pod, separated by the distance traveled during each rotation. The November images show no such gaps. The jets from 3 Atlas are continuous. They extend smoothly outward for millions of kilometers. There are no obvious periodic features, no puffs, no gaps, corresponding to the rotation period. The structure is, to use the technical term, tightly columnated. The jets maintain their directionality over distances that represent weeks of travel time at cometary outflow velocities. How is this possible? One explanation involves the orientation of the rotation axis. If the axis happens to point toward or away from the sun, the illumination pattern on the surface would be roughly constant as the nucleus rotates. Polar regions would be either in constant sunlight or constant shadow. Jets emerging from these regions would not turn on and off with rotation. They would fire continuously. This geometric explanation works, but it requires a specific orientation. The probability of the rotation axis being aligned just right to produce continuous jets is not negligible, but it is another coincidence to add to the growing list. Another explanation involves the surface structure of the nucleus. Imagine ice deposits sitting in deep valleys surrounded by mountains that cast shadows. These deposits would only be illuminated when the sun is at specific angles, when it can peer over the mountain rims and reach the valley floors. The resulting outgassing would be highly localized and strongly dependent on the rotation angle. This mechanism could explain why jets point in particular directions, but it struggles to explain the smooth, continuous structure we observe. If outgassing is tied to specific illumination geometries, you would still expect periodic variation as the nucleus rotates. A third explanation, more speculative, suggests that the jet structures we see are not active jets at all. They might be the trails of fragments that broke off from the main nucleus during the perihelion passage. Each fragment, now separated from the parent body, would leave behind a trail of gas and dust as its own ices sublimate. The linear features in the images would then trace the paths these fragments have traveled, not the current direction of outgassing from the main nucleus. This fragmentation hypothesis has some observational support. The images show linear features extending in multiple directions, consistent with fragments departing on different trajectories, but it also raises questions. David J.W. and Jane Liu obtained images on November 11th, showing what appears to be a single intact nucleus. If 3 Atlas had fragmented extensively at perihelion, we would expect to see multiple bright sources, not one. The puzzle deepens when you consider the anti-tail features. These are jets pointing toward the sun in the direction where radiation pressure should be pushing material away. Standard comets sometimes show anti, but these are usually optical effects caused by viewing geometry. When we look at a comet's dust tail edge on, it can appear to point sunward, even though the particles are actually moving away from the sun. The 3I Atlas antitail does not fit this geometric explanation. The viewing angle from Earth after perihelion was not edge-on. The features pointing toward the sun appear to be real jets, material actually moving in the sunward direction against the radiation pressure that should be pushing it away. How does material move toward the sun? For dust particles, it cannot. Radiation pressure always pushes outward. But for gas molecules, the situation is different. Gas is not pushed by radiation pressure in the same way dust is. If the nucleus is outgassing strongly on its night side, the side facing away from the sun, the resulting jets would point sunward. The gas would be moving toward the sun because it was ejected from a surface facing the sun. But why would the night side be outgassing strongly? There is no solar illumination to sublimate, unless the heat conducted through the nucleus has created subsurface pockets of warm material. Lest the interior of 3I Atlas is somehow warmer than its surface, lest there is an internal heat source. I am reaching the edges of standard cometry physics. Here the observations do not fit neatly into any single model. Multiple mechanisms might be at work simultaneously, creating a complex pattern that no one theory can explain. And there is one more possibility, one that researchers are reluctant to discuss publicly, but cannot entirely dismiss. What if the jets are not natural outgassing at all? Technological thrusters produce columnated jets. They maintain directionality regardless of rotation because they are designed to do so. They can point in any direction, toward the sun or away, because their orientation is controlled, not determined by illumination geometry. I am not claiming this is the correct explanation. I am pointing out that it fits the observations at least as well as the natural alternatives. The jets from 3 Atlas behave in ways that COMET jets should not behave. They maintain structure over distances that should smear them out, point in directions that should not be illuminated. They show no evidence of the periodic variation that rotation should produce. The upcoming observations will be critical. High-resolution images from Hubble and Webb during the December close approach might reveal the fine structure of these jets. Spectroscopic measurements could determine the velocity of the outflowing material. If the jets are moving at 400 meters per second, consistent with thermal outgassing, that supports the natural interpretation. If they are moving faster, at speeds consistent with rocket exhaust, the implications would be profound. For now, we are left with images that show something no one expected: 7 jets emerging from an interstellar visitor, creating patterns that challenge our understanding of how comets work. Whatever 3 Atlas is, it is not behaving like the comets we know. The strange patterns do not stop with the jets, because on November 20th, another set of images revealed something even harder to explain. Features that form an X shape extending perpendicular to the sunline, tracing paths that might represent something breaking away from the main body, something that might still be out there, traveling alongside 3 Atlas on its journey toward Jupiter. X marks the spot, many objects, and the fragmentation debate. November 20th, 2025, for 15 Universal Time. The same team that captured the 7-jet structure 12 days earlier pointed their instruments at 3I Atlas once again. Michael Jagger, Gerald Riemann, and Enrico Prosperi stacked 20 exposures of 100 seconds each, building up enough signal to reveal faint features extending far from the nucleus. What they found made international headlines. The image shows 4 distinct linear features extending outward from the central brightness of 3 Atlas. 2 of them align with the sun, forming the familiar tail and anti-tail structure, but to others extend perpendicular to the sunline, creating a pattern that looks unmistakably like the letter X, an X-shaped pattern surrounding an interstellar object. The imagery alone is enough to fuel speculation. But the scientific questions these features raise are even more compelling than their visual appearance. What are these sideways lines? The simplest explanation, and the one most researchers initially favored, is that they are satellite streaks. Earth is surrounded by thousands of artificial satellites, and occasionally one will pass through a telescope's field of view during a long exposure. The satellite appears as a straight line crossing the image, and if the exposure is long enough, multiple satellites can create intersecting patterns.
Oh.
There is some support for this interpretation. A third linear feature appears near the bottom of the November 20th image, unconnected to the main X pattern. This third line has no obvious relationship to 3 Atlas and looks exactly like what you would expect from a satellite streak. But there are problems with dismissing all the features as satellite contamination. The lines forming the X are oriented symmetrically around the nucleus. They extend in opposite directions from the central brightness, as if they emerge from 3I Atlas itself, rather than simply passing through the field of view. The probability of 2 satellites happening to cross the exact center of the target object from opposite directions, creating a symmetric pattern, is low. Not impossible, but low. More troubling, similar X-shaped features appeared in earlier images. When NASA finally released the higher-reason images from the Mars Reconnaissance Orbiter, taken on October 2nd, while 3I Atlas was passing close to Mars, the high-resolution data showed something remarkable. The nucleus appeared surrounded by a glow that extended in multiple directions, forming a pattern that resembles the November 20th X shape. The high-rise observation was taken from Mars orbit. There are no Earth satellites near Mars. Whatever created the X pattern in the October high-rise image, it was not terrestrial satellite interference. So what are we looking at? One hypothesis suggests these linear features trace the paths of fragments that have broken away from the main nucleus. Comets do fragment, sometimes spectacularly. The gravitational stresses of a close solar passage can pull a nucleus apart. Thermal stresses from uneven heating can crack the surface and release chunks. Volatile pockets buried beneath the surface can explode outward, ejecting material at high velocity. If fragments departed from 3 Atlas near perihelion on October 29, they would have had about 3 weeks to travel outward by the time of the November 20th observation. At a separation velocity of 500 meters per second, a fragment would cover roughly 1 million kilometers in that time. That matches the scale of the features in the image. The geometry works. Fragments departing in opposite directions would create linear features extending perpendicular to the main tail axis. As each fragment moves through space, trailing its own small coma of sublimating gas, it leaves behind a faint streak that traces its path. Connect these streaks back to their origin, and you get an X centered on the nucleus. But fragments imply fragmentation. Fragmentation implies the nucleus is breaking apart. And breaking apart is exactly what the post-perihelion images do not show. David Jewett and Jane Liu, 2 of the world's leading comet researchers, obtained images of 3 Atlas on November 11th. Their data shows what appears to be a single coherent source, not multiple fragments, not a debris field. One object still intact, still traveling on its interstellar trajectory. So, we have a contradiction. The X pattern suggests material is departing from 3 Atlas in multiple directions. The direct imaging suggests the nucleus remains whole. How do we reconcile these observations? One possibility is that the fragments are too small to detect as separate sources. If they are Killam scale or smaller, they would appear as faint smudges that blend into the overall coma. Only their trails, the linear streaks of gas and dust they leave behind, would be visible at the distances involved. Another possibility is that what we are seeing is not fragments at all, but rather a complex outgassing pattern created by the unusual structure of the nucleus. If 3 Atlas has multiple active regions on its surface, each producing a columnated jet, the combined effect might create the appearance of linear features extending in various directions. The X would then be an artifact of jet geometry, not evidence of physical separation. A third possibility, the one that generates the most controversy, is that the linear features represent the paths of objects intentionally released from 3 Atlas. Small probes, perhaps, deployed near perihelion to take advantage of the sun's gravitational assist. These probes would be traveling alongside the parent body, gradually separating as their slightly different trajectories carry them apart. I want to be clear about the status of this hypothesis. It is speculation. There is no direct evidence that 3 Atlas is technological in nature. No radio signals, no laser pulses, no artificial materials detected in the spectrum. But there is also no definitive proof that it is natural. The unusual features we observe are consistent with both possibilities, and responsible science requires acknowledging that uncertainty. What would we expect to see if many objects were being released from 3 Atlas? First, the objects would need to be small enough to remain undetected as point sources in current imagery. Anything larger than a few kilometers would be visible as a separate brightness peak. Second, they would need to be traveling at velocities close to that of the parent body, separating slowly over time rather than rocketing away at high speed. Third, their trails would be oriented in directions that relate to the trajectory geometry, not randomly distributed. The X pattern satisfies all 3 conditions. The objects creating the linear features, if they exist, are below our detection threshold. Their separation velocities are consistent with the scale of the pattern, and their orientations align with perpendicular to the sunline. Exactly where you would expect to find objects deployed for maximum divergence from the parent trajectory. This is circumstantial evidence at best, but it is worth tracking. The monitoring campaign now underway will help resolve these questions. The International Asteroid Warning Network has observatories around the world contributing data on 3I Atlas through January 2026. If the X pattern features persist and evolve in ways consistent with physical objects moving through space, that would support the fragment or probe hypothesis. If they disappear or prove inconsistent between observations, satellite contamination becomes more likely. The December 19th close approach to Earth will be particularly valuable. At 269 million km, 3I Atlas will be closer than it has been since the Mars flyby. And Earth-based telescopes will have their best opportunity to resolve fine details in the Comet structure. If there are many objects traveling alongside the main nucleus, we might be able to detect them directly. There is also the question of what happens at Jupiter. If fragments or probes separated from 3 Atlas near perihelion, their trajectories would differ slightly from the parent body. Over the months between perihelion and the March 2026 Jupiter encounter, these slight differences would compound. Objects that started close together would spread apart. By the time they reach Jupiter space, they might be millions of km from each other. This is where the Hill radius coincidence becomes relevant again. If the parent body passes just outside Jupiter's gravitational capture zone, smaller objects with slightly different trajectories might pass just inside. They might have enough relative velocity to enter orbit. They might end up as permanent residents of the Jupiter system, while the main body continues on its interstellar path. I keep returning to this scenario because it is both speculative and physically plausible. It requires no new physics, no violations of known laws. It only requires that 3I Atlas is more than it appears to be. That the object we are tracking is not just an inert chunk of interstellar ice, but something with a purpose we have not yet understood. The fragmentation debate will continue until we have more data. Right now, the evidence is ambiguous. X-shaped features that might be satellite streaks or might be fragment trails. A nucleus that appears intact in some images and surrounded by departing material in others. A trajectory that brings all of this to Jupiter's doorstep in March. What we need is time, more observations, and the willingness to follow the evidence wherever it leads. Because if many objects are separating from 3I Atlas, they are doing so now. Every day that passes, they travel farther from the parent body. Every day that passes, their trajectories diverge. By the time we reach December 19th, the separation might be large enough to detect, and if we detect them, everything changes. But detection requires knowing what to look for. It requires understanding the mass budget of 3 Atlas. The question of how much material should be surrounding it versus how much we actually see, and that mass budget reveals another puzzle. Perhaps the deepest puzzle of all. The missing mass paradox. Where did billions of tons go? Physics does not lie. Momentum is conserved. When gas escapes from a comet, the comet recoils. The force pushing the nucleus forward equals the force pushing the gas backward. This is Newton's third law, tested and verified in countless experiments over 3 centuries. It is as reliable as any law in science. This law creates a problem for 3 Atlas. It's a very big problem. Let me walk you through the calculation. the non-gravitational acceleration measured by NASA's jet propulsion. Laboratory during the perihelion passage amounted to approximately 0.02 millimeters s squared. That is a tiny acceleration, barely perceptible, but apply it over weeks, and it adds up. To create this acceleration throughout gassing, the nucleus must eject mass. The relationship is straightforward. Acceleration equals the mass ejection rate, time the ejection velocity divided by the total mass. Rearrange the equation, and you can calculate how much mass must be lost to produce the observed acceleration. The ejection velocity for sublimating ice is about 400 meters per second at the temperatures 3 Atlas experience near the Sun. This is the thermal velocity of gas molecules at around 200 Kelvin, a well-understood value based on decades of cometry observations. The total mass of 3 Atlas is harder to determine, but we have constraints. Before perihelion, from May through September, the object showed no detectable non-gravitational acceleration, despite ongoing outgassing. The James Webb Space Telescope measured a mass loss rate of about 150 kilograms per second in early August. This mass loss should have produced acceleration, yet none was detected. The only way to reconcile no detected acceleration with ongoing mass loss is if the mass of 3 Atlas is very large enough that 150 kilograms per second makes a negligible difference. Avib and his collaborators calculated the minimum mass required to explain this non-detection. The answer, at least 33 billion tons. That makes 3I Atlas a monster, about 1 million times more massive than the first interstellar object. About 1,000 times more massive than the second. Boris. For an object with a diameter estimated between 400 meters and 5 kilometers, 33 billion tons implies a density higher than solid rock. This is already anomalous. Interstellar comets should be porous, fluffy aggregates of ice and dust, not dense solid bodies. But the real problem comes when we apply the mass to the perihelion acceleration. If 3I Atlas has a minimum mass of 33 billion tons and experienced a non-gravitational acceleration of 0.02 millimeters s squared, the momentum equation tells us how much mass must have been ejected. The answer is staggering. At least 10 to 15% of the total mass, depending on the exact ejection velocity assumed. 15% of 33 billion tons is about 5 billion tons. 5 billion tons of material should have been blasted into space during the perihelion passage. 5 billion tons of gas and dust expanding outward from the nucleus, forming a massive cloud that would scatter sunlight and glow brilliantly against the darkness of space. Where is it? The post-perihelion images show 3 Atlas surrounded by a coma. They show jets extending in multiple directions. They show tail and anti-tail features reaching out for millions of kilom. But the total mass in these features, estimated from their brightness, falls far short of 5 billion tons. Far, far short. The visible material around 3 Atlas after perihelion amounts to perhaps tens of millions of tons at most. That is less than 1% of what the momentum calculation requires. 99% of the mass that should have been ejected is missing. This is the missing mass paradox. There are several possible resolutions, none of them entirely satisfactory. The first possibility is that the mass estimate is wrong. Maybe 3I Atlas is not as massive as the perihelion NAN detection suggests. Maybe the early outgassing was happening in a direction that canceled out, producing no net acceleration even though mass was being lost. If the true mass is much lower than 33 billion tons, then the required mass loss at perihelion would also be lower. But this explanation has its own problems. The lack of detected acceleration from May through September was very precisely measured based on over 4,000 observations from 227 observatories. To explain this non-detection with a less massive object, you would need extraordinary geometric fine-tuning. The outgassing would have to be almost perfectly symmetric. Jets firing in opposite directions with nearly identical thrust, canceling each other out to high precision. This seems unlikely for a natural object. The second possibility is that the ejection velocity is higher than expected. If gas is leaving 3 Atlas at 1,000 meters per second instead of 400, the required mass loss drops proportionally. Higher velocity means each kilogram of gas carries more momentum, so fewer kilograms are needed to produce the same acceleration. There is a natural mechanism that could produce higher velocities. Carbon monoxide ice sublimates at lower temperatures than water or carbon dioxide, and the resulting gas molecules move faster. If 3 Atlas is rich in carbon monoxide, as some spectroscopic evidence suggests, the outgassing might occur at velocities closer to 600 or 800 meters per second, but even doubling the ejection velocity only has the required mass loss. You still need billions of tons to explain the perihelion acceleration, and you still do not see billions of tons in the images. The third possibility is more exotic. What if the acceleration is not caused by outgassing at all? Technological propulsion could produce the observed acceleration with far less mass. Rocket engine expelling gas at 3 kilometers per second would need only about 3% as much propellant as sublimating ice to achieve the same thrust. An ion engine with exhaust velocities of 30 kilometers per second would need only about 1%. This is not evidence that 3I Atlas has an engine, but it is a mathematically consistent explanation for the missing mass. If the acceleration comes from technology rather than sublimation, the mass budget problem disappears. I realize this sounds outlandish. I am a scientist trained to favor natural explanations, to apply Occam's razor to resist extraordinary claims. But I am also trained to follow the data, and the data shows a deficit. Mass that should be there is not there. Whatever explanation we eventually accept will need to account for this deficit. Let me offer one more natural possibility before we move on. Perhaps the mass is there, but we cannot see it. Cometary outgassing produces a mixture of gas and dust. Gas is largely invisible to optical telescopes, does not scatter sunlight efficiently. Only specific wavelengths, emission lines from particular molecules, reveal its presence. Dust, by contrast, scatters sunlight broadly and produces the visible glow we associate with cometry. Comet, 3 Atlas ejected material that is predominantly gas with very little dust. The cloud could be more massive than it appears. The radio observations from MERCAT detected hydroxyl molecules, confirming that gas is present. But quantifying the total gas mass from radio absorption lines is difficult. The numbers have large uncertainties. Could billions of tons of invisible gas be surrounding 3I Atlas right now, undetected because we are not observing at the right wavelengths? It is possible. But the spectroscopic observations from Webb and Spherics should have detected signatures of such a massive gas cloud. The carbon dioxide emission at 4.3 micrometers, the water signatures at 2.7 micrometers. These would all be enhanced if the gas mass were much larger than currently estimated. So far, the spectroscopy does not support a hidden massive cloud. We are left with a puzzle that has no clean solution. The non-gravitational acceleration is real. The momentum calculation is straightforward. The mass deficit is genuine. Something does not add up. In the coming weeks, more observations will refine our estimates. The Hubble and Webb telescopes will observe 3I Atlas near its December 19th closest approach to Earth. Spectrometers will measure outgassing rates with higher precision. EMAG will track the evolution of the coma and jets. Perhaps the missing mass will reveal itself. Or perhaps the discrepancy will persist. Perhaps we will be forced to consider explanations that lie outside our comfortable models. Perhaps 3I Atlas is telling us something about itself that we are not yet ready to hear. The universe is vast, and our experience of it is limited. We have observed 3 interstellar objects in the history of astronomy. That is not much of a sample. If one of them turns out to be profoundly unusual, should we be surprised? I think of the missing mass paradox as an invitation to look more carefully, to question our assumptions, to consider possibilities we might otherwise dismiss. The data is telling us that something does not fit. Our job is to figure out what. And while we puzzle over the mass budget, another instrument was listening. Listening at radio frequencies that have special significance in the search for extraterrestrial intelligence. Listening at the frequencies where water molecules announce their presence. Listening at the exact frequencies where, in 1977, the Big Ear telescope detected a signal so unusual that the astronomer who found it wrote a single word in the margin of the printout. Wow. Radio whispers at the waterhole. MERCAT's historic detection. In the quiet hours of October the 24th, 2025, 64 dish antennas in the South African Coos stood aimed at a patch of sky just 3.76 from the sun. The MERCAT radio telescope, one of the most sensitive radio arrays on Earth, was hunting for something it had never detected before. Radio waves from an interstellar object. 5 days before perihelion, 3 Atlas was racing toward its closest approach to our star. Heating up, outgassing, transforming from a frozen wanderer into an active body shedding material into space, and Mercat was listening. What it heard was simultaneously exciting and, for those hoping for something more, sobering. At frequencies of 1,665 MHz and 1,667 MHz, the telescope detected absorption features, narrow dips in the radio spectrum at precisely the wavelengths where hydroxyl radical zoomolecules absorb background radiation. The Doppler shift of these features, about 1.5 kilometers per second, matched exactly what you would expect given the velocity of 3I Atlas relative to Earth on that date. The first radio detection of an interstellar object. But before you let your imagination run wild, let me explain what this detection means. Hydroxyl is a simple molecule, one oxygen atom bonded to one hydrogen atom. It forms when water ice sublimates, and the resulting water vapor is broken apart by solar ultraviolet radiation. O is in effect a calling card for water activity. Every comet that passes close enough to the sun to sublimate its water ice produces hydroxyl radicals. They are as natural as the sunrise. The Mercat detection tells us that 3I Atlas is outgassing water, or at least material that produces hydroxyl when hit by solar radiation. This is normal comet behavior. Expected, predicted. The fact that Mercat detected it confirms that 3I Atlas, whatever else it might be, is doing what comets do. Case closed? Not quite. The frequencies at which hydroxyl appears, 1665 and 1667 MHz, fall within a range of the radio spectrum that has special significance. Astronomers call it the water hole. This is the quiet zone between the emission lines of hydrogen at 1420 MHz and the hydroxyl lines at 1720 MHz. Radio noise from natural sources is relatively low in this range, making it an ideal frequency band for interstellar communication. The logic goes like this. Hydrogen is the most abundant element in the universe. Hydroxyl combined with hydrogen makes water, the solvent of life as we know it. Any technologically sophisticated civilization would likely recognize the significance of water, and they would recognize that the radio frequencies bracketed by hydrogen and hydroxyl constitute a natural meeting point, a galactic water hole where intelligent species might gather to exchange information. This idea has been around since the 1971 Cyclops study, a NASA-funded analysis of how we might search for extraterrestrial intelligence. The water hole concept shaped decades of SETI research. It is the reason the Big Ear telescope was monitoring frequencies near 1420 MGHz on August 15th, 1977, when it detected the famous WOW signal. And here's where things get interesting. The arrival direction of 3 Atlas coincides within 9 of the direction from which the WOW signal came. Both originate from the general direction of the constellation Sagittarius. Both involve radio frequencies in or near the water hole. And now, 3 Atlas has produced a radio detection at water hole frequencies just days before its closest approach to the sun. Coincidence piles upon coincidence. Need to be careful here. The Mercat detection is hydroxyl absorption, not emission. It is a natural phenomenon produced by cometary outgassing, not a technological transmission. The Doppler shift, the line widths, everything about the signal is consistent with standard cometary physics. There is nothing in the data that requires an artificial explanation. But Avi Loeb, who had encouraged Mercat to observe 3I Atlas at radio wavelengths, made an interesting point. The detection occurred only on October 24th. Earlier attempts on September 20th and September 28th failed to detect any hydroxyl signal. The O appeared suddenly just days before perihelion, when outgassing activities should have been increasing rapidly for E natural comet. This is expected behavior. As the nucleus heats up approaching the sun, sublimation increases. More water vapor means more hydroxyl. The October 24th detection simply reflects the increased activity of an object responding to solar heating. But Lowe asks a different question. How do we know the hydroxyl production is constant? What if it varies in ways we have not yet measured? What if there are intermittent periods of enhanced activity that we might mistake for natural variation, but that actually reflects something else? He is not claiming 3 Atlas is sending signals. He is pointing out that we do not have enough data to fully characterize its radio behavior. He is calling for continued monitoring, more observations, a complete picture of how this object interacts with the electromagnetic spectrum. Fair enough. That is how science works. You observe, you record, you look for patterns, and you remain open to surprises. On November 5th, Mercat conducted another observation. This time, specifically searching for narrowband radio transmissions, the kind of signals that artificial sources produce, the kind of signals that SETI researchers have been hunting for decades. The Blue's back end, a real-time techno-signature detection system, analyzed the data. The result: 23,689 candidate signals detected. Every single one traced back to terrestrial radio frequency interference, human-made sources that happened to fall within the telescope's field of view. None of them originated from 3I Atlas. The detection limit for this observation was about 0.17 W. That is roughly the power output of a cell phone handset at the distance of 3I Atlas, approximately 334 million km. If there was any technological radio transmission coming from the interstellar visitor, it was either off during the observation or too weak to detect. This is not conclusive. Absence of evidence is not evidence of absence. A transmitter could have been silent on November 5th. It could operate at frequencies outside Mercat's range. It could use communication methods we do not recognize as signals. It cannot prove the negative, but the combination of data is informative. Hydroxyl detected, consistent with natural water outgassing. No artificial signals detected above the noise floor. The simplest interpretation is that 3 Atlas is exactly what it appears to be, a comet. An unusual comet from interstellar space, to be sure, but a comet nonetheless. And yet, the water hole connection lingers. The near coincidence with the WOW signal direction lingers. The strange jets, the missing mass, the trajectory anomalies, they all linger. Each individual observation has a natural explanation, but the totality of observations creates a pattern that resists easy dismissal. Let me tell you about the WOW signal connection in more detail because it keeps coming up in discussions of 3 Atlas. On August 15, 1977, the Big Ear radio telescope in Ohio recorded a 72-second burst of radio energy at 1,420.456 MHz. The signal was strong, more than 30 times louder than the background noise. It came from the direction of Sagittarius, and it never repeated. Jerry Eman, the astronomer who discovered it while reviewing the printout, wrote a single word in the margin. Wow. The name stuck. For nearly 50 years, the WOW signal has remained unexplained. Hundreds of follow-up observations have failed to detect anything similar from the same region of sky. Various natural explanations have been proposed: comets releasing hydrogen, magnetars flaring, interstellar scintillation effects. None have been fully satisfactory. The connection to 3I Atlas was noted by Liu early in the observing campaign. The interstellar object's incoming trajectory traces back to a region of the sky separated by only 9 from the WOW signal source. In the vastness of the celestial sphere that is remarkably close, could they be related? Could the WOW signal have been a transmission from whatever civilization, if any, sent 3I Atlas? Could this be a 48-year-old calling card finally receiving its follow-up? The timing would be extraordinary. The WOW signal occurred in 1977. 3E Atlas arrived in 2025. The interstellar object was traveling at roughly 200 kilometers per second during its approach. At that speed, covering the distance from the WOW signal source to our solar system would take far longer than 48 years. Millions of years depending on the assumed distance. So a direct connection where the WOW signal was sent by 3 Atlas itself does not work mathematically. The object was nowhere near our solar system in 1977, but an indirect connection is possible if 3II Atlas originates from the same region of the galaxy as the WOW signal source. If both are associated with some distant civilization or phenomenon in the direction of Sagittarius, the coincidence might be meaningful. Not as cause and effect, but as parallel manifestations of something happening in that part of the sky. I am speculating wildly now. This is the kind of connection that fires the imagination, but cannot be tested with current data. We do not know where the WOW signal came from. We do not know where 3 Atlas originated beyond the general direction of its approach. The 9 angular separation might mean everything or nothing. What we can say is that the radio observations of 3 Atlas have added another layer to an already complex story. The object is active at radio wavelengths, produces hydroxyl in the water-hole frequency range. It does not appear to be transmitting artificial signals, and its approach direction near the WOW signal source remains an unexplained curiosity. The monitoring continues. March 2026 will bring the Jupiter encounter, and NASA's Juno spacecraft will use its radio instruments to observe 3I Atlas from a distance of about 53 million kilometers. If there are radio signals to be detected, signals and frequency ranges that MERCAT cannot access, Juno might find them. Till then, we watch, we listen, we collect data, and we remain open to the possibility that the universe might still surprise us. Because while the radio observations tell one story, the optical images tell another. NASA sat on some of the most important images for over 40 days, delaying release until public pressure forced action. And when those images finally emerged, they revealed details about 3 Atlas that no one had seen before. Details captured from the only spacecraft that got truly close to the interstellar visitor, the HiRISE revelation, what NASA's Mars images finally showed. For 43 days, the images sat locked in a bureaucratic limbo. The government shutdown that began on October 1, 2025, had frozen NASA operations. Websites stopped updating, press releases stopped flowing, and some of the most important astronomical data of the decade remained inaccessible to the scientific community. The HiRISE camera aboard the Mars Reconnaissance Orbiter had captured 3I Atlas on October 2nd and 3rd, when the interstellar object passed within 29 million kilometers of the red planet. This was the closest any spacecraft would get to 3 Atlas during its entire journey through our solar system. The spatial resolution, about 30 kilometers per pixel, was 3 times better than what Hubble could achieve from Earth orbit. These images would reveal details invisible to any other instrument, and they were stuck behind a shutdown. Congresswoman Anna Paulina Luna sent a letter to NASA's interim administrator, Shaw Duffy, demanding the release. The scientific community, led by vocal researchers like Avi, made the case publicly. 40 days of delay during a once-in-a-lifetime observing opportunity was unacceptable. Scientific knowledge should not be hostage to bureaucracy. Finally, on November 19th, NASA held a press conference. The images were released, and what they showed was both revealing and frustrating. The HiRISE image of 3 Atlas appears as a fuzzy white ball against the darkness of space. Due to spacecraft jitter during the observation period, the target is smeared across several pixels. The bright inner region of the coma is visible, but the fine structure that everyone hoped to see remains blurred. No sharp edges, no resolved nucleus, just a glowing blob that tells us less than we wanted to know. Even this imperfect image carries information. The full coma of 3 Atlas spans the entire HiRISE field of view. Only the brightest inner region is detectable given the exposure time used, but the glow extends far beyond what the image captures. This confirms that 3 Atlas was surrounded by an extensive cloud of material during its Mars flyby, consistent with active outgassing. The shape of the coma is not symmetric. There appears to be extension in multiple directions, hints of the jet structure that would become more prominent in post-perihelion observations. The X-shaped pattern that later appeared in Earth-based images may have been forming already during the Mars encounter. More valuable than HiRISE alone was the combination of Mars-based observations. NASA's MAVEN orbiter used its imaging ultraviolet spectrograph to observe 3I Atlas on September 28th. The ultraviolet data revealed hydrogen atoms surrounding the comet, the signature of water ice sublimating and breaking apart in sunlight. The MAVEN image shows 3 distinct sources of hydrogen. 3 Atlas itself, appearing as a dim spot on the left, Mars appearing as a bright streak on the right, and interplanetary hydrogen flowing through the solar system as a dimmer streak in between. This ultraviolet detection provided early confirmation that 3 Atlas was actively outgassing water, complementing the later radio detection of hydroxyl by MERCAT. The consistency between ultraviolet and radio observations strengthens our confidence that water activity is genuine. On October 4th, the Mars rover exploring the rim of Jezero crater turned its MASTAMS instrument toward the sky. The exposure had to be exceptionally long to detect such a faint object. Unlike telescopes that track moving targets, Mascom Z is fixed during long exposures. The result is an image where stars appear as streaks dragged across the frame by the motion of Mars, while 3 Atlas appears as a faint smudge, barely perceptible against the background. This is the first time a rover on another planet has photographed an interstellar object. The historical significance is profound, even if the image itself is modest. We are building a catalog of observations from multiple vantage points across the solar system, each adding a piece to the puzzle. But the Mars observations also raised questions that remain unanswered. During the government shutdown, while NASA was unable to release high-rise data, China's National Space Administration published images from its own Mars orbiter, 1011, the high-resolution imaging camera aboard Tian. When captured 3 Atlas on October 3rd, from a distance of about 29 million kilometers, the Chinese images show a nucleus surrounded by a coma several thousand km in diameter. An animation created from a series of 30-second exposures tracks the motion of 3 Atlas across the Martian sky. The data is lower resolution than high-rise would provide, but it was available. It showed the world what NASA was sitting on. The contrast was stark. One space agency sharing data in real time, another holding it hostage for bureaucratic reasons. The scientific community noticed. When NASA finally released its full package of observations on November 19th, the presentation emphasized the cometary nature of 3I Atlas. NASA planetary scientist Tom Statler explicitly addressed the rumors that had been circulating. "The object looks and behaves like a comet," he said. "All evidence points to it being a comet. This is accurate as far as it goes." The images show a coma. The spectroscopy shows outgassing. The radio observations show hydroxyl. Everything is consistent with cometary activity, but everything is also consistent with something more complex. The images do not show the nucleus directly. They show scattered light from the coma. We still do not know the exact size of the nucleus, only upper limits based on brightness. We still do not know its shape. We still do not understand the mechanism driving the unusual jet structure. What the Mars images tell us is that 3 Atlas was already active in early October, well before perihelion. The material surrounding it was already extensive. The processes that would produce the post-Pallian mysteries were already underway. And there was another observation from Mars that deserves attention. ESA's ExoMars Trace Gas Orbiter observed 3I Atlas between October 1st and 7th. This European spacecraft, designed to study the Martian atmosphere, turned its instruments toward the interstellar visitor. The data from TGO provided something unexpected, a dramatic improvement in trajectory precision. Usually, orbit determination relies on observations from Earth. Ground-based telescopes measure positions against the background stars, and these measurements are combined to calculate trajectories. The precision depends on the number and quality of observations and on the geometry of the viewing angles. Adding TJO data from Mars orbit introduced a new geometry. Suddenly, astronomers had simultaneous observations from 2 different planets, allowing triangulation. The result was a 10-fold improvement in trajectory accuracy, reducing the uncertainty in 3 Atlas's predicted position from several hundred km to just tens of km. This improved precision matters for the Jupiter encounter calculations, matters for understanding whether the trajectory passes inside or outside the Hill radius, and it matters for planning future observations during the December 19th close approach to Earth. The Mars observations taken together paint a picture of an object doing exactly what a comet should do: outgassing water and carbon dioxide as it heats up approaching the sun, developing a coma and jets as volatiles, escape the surface following a trajectory that responds to both gravity and the gentle push of escaping gas. If you stopped here, you would conclude that 3E Atlas is simply an unusual comet from interstellar space. Unusual in its size, its speed, its composition, but fundamentally natural. A frozen relic of planet formation around another star, ejected into the void billions of years ago, and now passing through our corner of the galaxy by chance. But you cannot stop here, because the Mars observations occurred before perihelion, before the non-gravitational acceleration was measured, before the missing mass paradox emerged, before the 7 jets and the X-shaped features appeared. The Mars data shows 3I Atlas in a relatively quiet state. What came after was anything but quiet. The 43-day delay in releasing the high-rise images meant that, by the time we saw the Mars data, 3E Atlas had already transformed. The post-perihelion object is different from the prep-perihelion object, more active, more structured, more anomalous. And now the scientific community is preparing for the next major observation window. The December 19th close approach to Earth will bring 3IE Atlas II within 269 million km of our planet, closer than it has been since leaving Mars behind. Hubble and Webb will observe. Ground-based observatories around the world will track its motion. The IWN campaign will collect data from hundreds of instruments. This will be our best chance to understand what 3 Atlas really is, our best chance to resolve the anomalies, to explain the missing mass, to characterize the jets in detail. The data we collect in December will shape our understanding of this interstellar visitor for decades to come. Because after December 3, I-Atlas begins its long journey outward toward Jupiter in March. Then beyond, into the darkness between the stars, never to return. We have a few months of observation time left, and then this visitor will be gone forever. The Mars images gave us a preview. The December observations will give us the final word, or at least the final word that Earth-based science can provide. What happens at Jupiter and what happens after remains to be seen. The United Nations thinks this matters enough to prepare. For the first time in history, the International Planetary Defense Network has activated a formal exercise around an interstellar object. And the timing of this exercise is no accident. EON activates the United Nations Planetary Defense Drill. On November 27, 2025, something unprecedented began. The International Asteroid Warning Network, a United Nations-endorsed collaboration of space agencies and observatories from around the world, formally activated an observing campaign targeting 3I Atlas. This is the 8th such exercise since EON was established in 2017, but it is the first to focus on an interstellar object. The timing is not coincidental. Let me explain what IIAPN is and why it exists. The network was established under the auspices of the United Nations Office for Outer Space Affairs, UNUSA, to coordinate the global response to potential asteroid and comet threats. Its partner organization, the Space Mission Planning Advisory Group, or SEMAG, handles the mission planning side, designing the spacecraft and interventions that might someday be needed to deflect a threatening object. Together, these organizations form the backbone of humanity's planetary defense infrastructure. They are the reason we have early warning systems. They are the reason we know what is out there. And they are the reason that if something dangerous ever does head our way, we will not be caught off guard. JON conducts regular exercises to test its capabilities. These exercises typically target near-Earth asteroids, objects on trajectories that bring them close to our planet. The goal is to practice the coordination and communication that would be essential in a real emergency, which observatories can contribute. How quickly can data be shared? How accurately can orbits be determined? These are questions that must be answered before a crisis, not during one. The 3I Atlas campaign is different. This interstellar visitor poses no threat to Earth. Its closest approach of 269 million km keeps it safely distant. There is zero probability of impact. So why is EON treating it as an exercise target? The official documentation is clear. Comets present unique challenges for accurate astrometric measurements and orbit predictions. The extended morphology, the coma, and tails can pull centered measurements away from the true center of the nucleus. For Earth-threatening comets, getting the orbit right is critical. A small error in position can translate to a large error in impact probability. ION wants to practice on a difficult target. 3 Atlas is certainly difficult. Its hyperbolic trajectory, with an eccentricity of about 6.14, is steeper and faster than any solar system comet. Its active coma, now showing multiple jets and complex structure, makes precise position measurements challenging. Its interstellar origin means we have no historical observations to anchor the orbit. It is, in short, an ideal stress test for planetary defense capabilities. The campaign runs from November 27, 2025, through January 27, 2026. The schedule includes a mid-sea campaign review on December 9th and a wrap-up. Teleconference on February 3rd. Observatories around the world have registered to participate, contributing data in the standardized ATIS format that allows seamless integration. But here's the thing about exercises. They are not just practice, they generate real data. They involve real analysis, and sometimes they reveal things that were not expected. The I-Dublin campaign will produce the most comprehensive dataset ever collected on 3I Atlas. Thousands of observations from hundreds of telescopes spanning 2 months of the object's journey outward from the Sun. This dataset will be used to refine trajectory models, characterize outgassing behavior, and resolve questions about the object's physical properties. If there are anomalies in the data, this campaign will find them. If the trajectory deviates from predictions, this campaign will measure the deviation. If 3I Atlas does something unexpected, this campaign will document it. And the timing places the December 19th close approach right in the middle of the observing window. I want to address the sensational headlines that accompanied the AVAN announcement. Some outlets reported that NASA had activated planetary defenses against 3I Atlas. Others implied that the exercise reflected secret concerns about the object's true nature. None of this is accurate. Ian has been planning a full 2025 Comet campaign since 2024. The network needed a practice target, and 3-2 Atlas happened to arrive at the perfect time. The decision to use the Interstellar visitor as the exercise subject was opportunistic, not reactive. There are no hidden concerns. There is no secret threat assessment. This is exactly what it appears to be, a rare opportunity to practice on a scientifically interesting object. That said, the exercise does reflect something important about how seriously the international community takes planetary defense. We live in an era of unprecedented awareness about cosmic threats. The DART mission demonstrated that we can deflect an asteroid. The Vera Rubin Observatory, coming online soon, will detect near-Earth objects at unprecedented rates. The NEO Surveyor mission, once fully operational, will survey the infrared sky for threatening asteroids invisible to optical telescopes. These capabilities are being built because we understand the risk. Major asteroid impacts have happened in Earth's past and will happen again in Earth's future. The question is not whether a dangerous object will someday threaten us, but when. And when that day comes, we need to be ready. The 3I Atlas exercise is part of that preparation. It tests coordination. It tests communication. It tests the ability of the international community to focus resources on a target that matters. The lessons learned will apply to future encounters with objects that pose real danger. But there is another layer to consider. Interstellar objects represent a different category of challenge. Solar system asteroids and comets have orbits we can track over decades, can predict their positions years in advance, have time to plan responses if one threatens impact. Interstellar visitors arrive unannounced, moving at speeds that give us little reaction time. 3E Atlas was discovered on July 1, 2025, when it was already inside Jupiter's orbit. From detection to perihelion was only 4 months. If an interstellar object were on a collision course with Earth, we might have only months of warning, possibly less. The All-Win exercise is in part a chance to practice responding to that scenario. How quickly can we characterize a fast-moving target? How accurately can we predict its trajectory? How effectively can we coordinate a global response? 3 Atlas, safely passing at a great distance, lets us practice without the pressure of a real emergency. The next interstellar visitor might not be so cooperative. I keep returning to the statistical argument that Avi and others have made. We have detected 3 interstellar objects in the history of astronomy. Mu in 2017, Boris in 2019, and now 3 Atlas in 2025. That is not many. And all 3 have been unusual in some way. Mu showed non-gravitational acceleration without any visible outgassing. It's had an extreme aspect ratio, appearing to tumble through space like a thin disk or elongated cigar. Its trajectory passed close to Earth, as if it were targeting our planet for observation. No satisfactory natural explanation has emerged. Boris was more straightforwardly commentary, showing classic activity and composition, but its size and speed were notable. It passed through the inner solar system quickly, giving us limited observation time. 3I Atlas is larger than both by orders of magnitude, moves faster than both, shows anomalies that neither of its predecessors displayed. And its trajectory brings it to Jupiter's gravitational doorstep under circumstances that stretch Creddle. 3 objects do not make a pattern. But if interstellar visitors continue to arrive with unusual properties, at some point we need to ask why. Is our detection capability biased towards certain types of objects? Are we missing the ordinary ones and only catching the strange ones? Or is there something genuinely anomalous about the interstellar population? The Alvin campaign will contribute data that helps answer these questions, not definitively perhaps, but incrementally. Each observation adds to our understanding. Each measurement constrains our models. Over time, a clearer picture will emerge. For now, the exercise serves its immediate purpose. Observatories are coordinating. Data is flowing. Trajectory refinements are being computed. The international community is practicing for a day we hope never comes. And in the midst of this practice, 3I Atlas continues its outward journey past the orbit of Mars, toward the asteroid belt, toward Jupiter, each day a little farther from the Sun, each day a little closer to its March encounter with the solar system's giant. The next milestone is December 19th, the day 3 Atlas reaches closest approach to Earth, the day when our telescopes will have their best view, the day when questions might finally be answered, or when new questions might arise. December 19th. The countdown to Earth's closest encounter. In 21 days from today, 3I Atlas will reach its closest approach to Earth, 269 million km, 1.88 astronomical units, nearly twice the distance from here to the Sun. But closer than this interstellar visitor has been since passing Mars in early October, this is our moment. Our best chance to study an object from another star system. Our final opportunity before 3 Atlas recedes into the outer solar system and eventually disappears beyond our reach forever. The astronomical community is preparing. Hubble Space Telescope has observation time scheduled. The venerable Orbital Observatory, now operating for over 35 years, will train its cameras on 3 Atlas during the close approach window. Hubble's resolution at optical wavelengths remains unmatched by ground-based telescopes, even with adaptive optics. The images it captures will reveal fine structure in the coma and jets that cannot be seen from Earth's surface. The James Webb Space Telescope will observe as well. Webb's infrared instruments are uniquely capable of measuring the chemical composition of the outgassing material. The spectra from Webb will tell us what ices are sublimating, at what rates, and in what proportions. The August observations already revealed the carbon dioxide-dominated nature of 3 Atlas. December observations will show how that composition has evolved after perihelion. Ground-based observatories around the world are scheduling time. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gemini telescopes in both hemispheres. Amateur astronomers with backyard instruments are planning their observing sessions. 3E Atlas, now at about magnitude 10, is visible with modest equipment under dark skies. But visibility comes with constraints. 3 Atlas is currently in the morning sky, rising a few hours before dawn. Observers need to catch it during the window between its rise and the brightening of morning twilight. As December progresses and the object moves higher in the sky, the observing window will improve. By closest approach, conditions should be favorable for extended observation sessions. The Virtual Telescope Project has announced a live-stream event for December 19th. Gianluca Massi and his collaborators in Manciano, Italy, will broadcast real-time images as Earth passes its closest point to the interstellar visitor. Anyone with an internet connection will be able to watch this historic moment unfold. What do we hope to learn from the December observations? First, we want to understand the jet structure in detail. The post-perihelion images have shown complex patterns of jets and antitails, features that do not match the behavior of familiar comets. Higher resolution images during closest approach might reveal the origins of these jets. Are they emerging from discrete active regions on the nuclear surface? Are they fragments trailing behind the main body? Are they something else entirely? Second, we want to measure the outgassing rates precisely. The non-gravitational acceleration measured near perihelion implies substantial mass loss. By December, the object will be farther from the Sun and cooler. Outgassing rates should have decreased, but by how much? If the activity drops as expected for a natural comet following standard thermal models that supports the cometry hypothesis, if activity remains higher than expected, we will need to consider alternative explanations. Third, we want to search for fragments or companion objects. The X-shaped features in recent images hint at materials separating from the main nucleus. December observations with better resolution and sensitivity might directly detect these objects if they exist. Finding fragments would provide crucial information about the internal structure of 3 Atlas. Finding nothing would suggest the X features have other explanations. Fourth, we want to refine the trajectory for the Jupiter encounter. Every observation improves our orbital solution. The more precisely we know where 3I Atlas is now, the more accurately we can predict where it will be in March. The question of whether it passes inside or outside Jupiter's Hill radius depends on trajectory refinements that will continue right up until the encounter itself. The timing of closest approach creates an interesting observational geometry. December 19th falls just days before the winter solstice in the northern hemisphere. Nights are long, the sun sets early and rises late. For observers at northern latitudes, this provides extended dark sky time, maximizing the opportunity to observe 3I Atlas as it crosses the constellation Leo. The moon's phase is also favorable. On December 19th, the moon will be in its waning crescent phase, rising in the pre-dawn hours, well after 3I Atlas has crossed the meridian. Moonlight will not interfere with observations of the relatively faint comet. Nature is cooperating. The conditions for observation could hardly be better, and yet there is urgency. 3 Atlas is moving fast. Its hyperbolic trajectory carries it outward at tens of kilometers. Every day after a closest approach, it will be farther away. Every day the angular size will shrink. Every day the brightness will fade. The window for detailed observation is measured in weeks, not months. In mid-January, 3I Atlas will have receded significantly. By early February, it will be entering the realm where only the largest telescopes can track it effectively. By March, when it reaches Jupiter, it will be so distant that Earth-based observations will struggle to resolve any structure at all. This is why December matters so much. This is why every clear night in the coming weeks represents an opportunity that cannot be recovered if lost. I want to take a moment to reflect on what we are witnessing. 3 Atlas is a messenger from another star. It has traveled for billions of years through the interstellar medium, a frozen wanderer, adrift in the darkness between suns. Whatever it is, wherever it came from, it carries information about a distant place and time that we cannot access any other way. The composition of 3 Atlas tells us about the proto-planetary disk where it formed, the ratio of carbon dioxide to water, the presence of carbon monoxide and other volatiles. These are fingerprints of the conditions that existed around its parent star billions of years ago. By studying this object, we learn about planet formation in other solar systems. We learn about the diversity of cosmic chemistry. We learn about ourselves by seeing what is different. And if 3I Atlas is something more than a natural comet, if the anomalies we have observed point towards something we do not yet understand, then December 19th becomes even more significant. It might be the moment when we glimpse the answer. It might be the moment when the mystery deepens. Either way, we will never be the same. The countdown continues. Every sunrise brings us closer to the encounter. Every sunset marks another day of observation opportunity. The data is accumulating. The models are being refined. The scientific community is focused on this single object with an intensity rarely seen in astronomy. Meanwhile, 3I Atlas itself remains silent. No radio signals, no laser pulses, no obvious signs of technology beyond the strange behaviors that have fueled so much speculation. It moves through our solar system, doing what comets do, shedding gas and dust, responding to the sun's warmth, following the laws of physics wherever they lead. Perhaps that is all there is. Perhaps 3 Atlas is exactly what it appears to be, an interstellar iceberg doing nothing more than sublimating in the solar heat. Perhaps the anomalies are artifacts of our limited understanding, gaps in our models that will be filled as we collect more data. Perhaps future textbooks will describe this as the third interstellar comet, notable for its size and composition, but fundamentally natural. Or perhaps not. The honest answer is that we do not yet know. December 19th, for all its importance, may not provide the definitive answer. Some mysteries take years to unravel. Some take decades. Some are never fully resolved. But we will have tried. We will have observed with every instrument at our disposal. We will have collected the best data our technology allows. We will have asked the right questions, even if the answers remain elusive. That is what science does. looks, it measures, it wonders, and sometimes it is surprised. December 19th is coming. The closest encounter is coming. And beyond that, the Jupiter flyby is coming. March 2026. The moment when 3 Atlas passes through Jupiter's gravitational neighborhood. And whatever questions remain about its trajectory, its mass budget, and its nature will face their final test beyond Jupiter. What March 20th, 26 will reveal. The giant planet waits. Jupiter, 2.5 times more massive than all other planets in our solar system combined, sits at 5 astronomical units from the Sun. Its gravity reaches across hundreds of millions of km, bending the paths of comets, capturing asteroids, shielding the inner solar system from bombardment. For 4.5 billion years, Jupiter has stood sentinel over our cosmic neighborhood. And in March 2026, Jupiter will have a visitor from the stars. 3E Atlas is on course to pass within approximately 54 million kilometers of Jupiter on March 16, 2026. That distance places it near the edge of Jupiter's Hill sphere, the boundary of gravitational dominance that we have discussed throughout this exploration. Whether it passes just inside or just outside that boundary depends on trajectory refinements that are still ongoing. What happens at Jupiter will tell us something profound about 3I Atlas. If the trajectory models are correct and the object passes outside the Hill radius, it will continue on its outbound journey, leaving the solar system forever. The gravitational influence of Jupiter will bend its path slightly, accelerating it in a slingshot maneuver that adds to its already formidable speed. By late 2026, 3I Atlas will be beyond Jupiter's orbit, heading toward the Kuiper Belt and eventually interstellar space. If something unexpected happens, if the trajectory deviates from predictions, if objects separate and enter Jupiter's gravitational influence, if any observation suggests behavior inconsistent with a natural comet, then we will face questions that science is not prepared to answer. NASA's Juno spacecraft will be watching. Juno has orbited Jupiter since July 2016, studying the giant planet's atmosphere, magnetic field, and interior structure. During the 3 Atlas encounter, Juno will be approximately 53 million km from the interstellar visitor. That is too far for detailed imaging, but close enough for other types of detection. Juno carries a radio instrument called WAVES that operates at frequencies from 50 Hz to 40 MHz. Till if 3 Atlas emits any radio signals in this range, Juno might detect them. The spacecraft was not designed for this purpose, but discovery often comes through serendipity. ESA's JUICE spacecraft, currently en route to Jupiter, will also be in the vicinity. JUICE is farther from 3I Atlas than Juno, but it carries a more comprehensive instrument suite. Its particle detectors might sense material shed by the interstellar visitor. Spectrometers might detect emissions we cannot observe from Earth. The data from JUICE is expected to arrive in February 2026. After the spacecraft adjusts its communication protocols for the deep space environment between Earth, Queen-based observations and spacecraft data, we will have multiple perspectives on the Jupiter encounter. If 3 Atlas does anything unexpected, we should see it. But what would unexpected look like? The most dramatic possibility would be a trajectory change. 3 Atlas adjusts its course near Jupiter. If the non-gravitational acceleration suddenly increases or changes direction, that would be difficult to explain with natural processes. Cometary outgassing is driven by solar heating, and by March 3, Atlas will be far enough from the Sun that volatile activity should have decreased substantially. Any significant course correction at that point would demand explanation. A more subtle possibility involves the release of smaller objects. We discussed the X-shaped features and the potential for fragments or probes separating from the main body. If such objects exist, and if their trajectories carry them into Jupiter's Hill sphere, they could become captured. They could establish orbits around Jupiter or its moons. They could remain in the Jupiter system long after the parent body has departed. Detecting such objects would be extraordinarily difficult. I think the distances involved, anything smaller than a few km, would be invisible to our telescopes. We would not see them during the flyby. We might not see them for years. But if they exist, they might eventually reveal themselves. Jupiter is well monitored. Its moons are studied intensively. Anything new appearing in the Jovian system would eventually be noticed. This is speculative territory. I want to be clear about that. There is no evidence that 3 Atlas has released probes, or that anything artificial is associated with its trajectory. These are possibilities, not facts. They are included here because responsible analysis requires considering all scenarios, not just the comfortable ones. The most likely outcome of the Jupiter encounter is that 3 Atlas will pass by uneventfully, continuing on its outbound trajectory, doing exactly what a natural comet would do. The scientific community will collect data, papers will be written, and eventually the object will fade from view, becoming just another point of light receding into the darkness. But even this mundane outcome carries value. 3 Atlas has already taught us about the interstellar population. We now know that interstellar objects can be significantly larger than or Borisov. We know they can show unusual compositions with carbon dioxide dominating over water. We know they can display non-gravitational acceleration while still exhibiting cometary activity. These findings reshape our understanding of what drifts between the stars. The Vera Rubin Observatory, expected to begin full operation soon, will detect many more interstellar visitors in the coming years. Its wide-field survey capabilities will catch faint, fast-moving objects that previous instruments missed. We may discover that 3 Atlas is unusual, a rare giant among smaller wanderers. Or we may discover that it is typical, one of many massive interstellar bodies that we simply had not noticed before. Either way, the knowledge we gain from studying 3I Atlas will inform our understanding of the entire interstellar population. It will help us prepare for future encounters. It will expand our conception of what is out there beyond the familiar borders of our solar system. And that brings me to the largest question of all. Why are we so fascinated by the possibility that 3 Atlas might be artificial? Part of the answer is obvious. The idea of extraterrestrial intelligence captures the human imagination like few other topics. We have wondered about life beyond Earth for millennia. The possibility that we might finally encounter evidence of another civilization, even in the form of an ancient probe drifting through our solar system, stirs something deep within us. But there is another dimension to this fascination. 3 Atlas challenges our assumptions about what is normal. Its trajectory is unusual. Its composition is unusual. Its jet structure is unusual. Its mass budget is unusual. Any one of these features might be dismissed as a quirk. Together, they form a pattern that demands attention. Science advances by taking anomalies seriously. Not by assuming they must be evidence of the extraordinary, but by investigating them carefully until they yield to explanation. Sometimes the explanation is mundane, a measurement error, a modeling assumption that needs revision, an overlooked physical process. Sometimes the explanation is profound, a new law of nature, a new class of objects, a new understanding of reality. We do not yet know which category 3I Atlas belongs to. The data is ambiguous. The models are imperfect. The observations are incomplete. We are in the early stages of understanding something that has never been observed before. That uncertainty is uncomfortable. We want answers. We want to know whether we are alone in the galaxy. We want to know whether interstellar visitors are benign or threatening. We want to know whether the universe makes sense. 3 Atlas does not provide those answers. Not yet. Maybe not ever. But it provides something equally valuable. It provides an opportunity to ask better questions, to look more carefully, to think more creatively, to confront the limits of our knowledge and push beyond them. That is what science is for. That is what this moment is for. 3 Atlas is leaving. Slowly but inextricably, it is moving away from the sun, away from Earth, away from the instruments that have studied it since July. Within a year, it will be gone, a receding point of light fading into the black. But the data it has provided will remain. The questions it has raised will remain. The sense of wonder it has inspired will remain. And somewhere in the direction of Sagittarius, other objects may be drifting. Other messengers from other stars, other mysteries waiting to be found. We will keep watching. We will keep wondering. We will keep asking whether we are alone. Thank you for joining me on this journey through the mysteries of 3 Atlas. If you found value in this exploration, please take a moment to like this video and subscribe to the channel. Your support makes this work possible. I want to remind you, as always, that the claims we have discussed tonight range from established scientific consensus to speculative hypothesis. Where uncertainty exists, I've tried to be transparent about it. Science is not about knowing everything. It is about acknowledging what we do not know and working to understand it better. The truth about 3 Atlas, Whatever that truth turns out to be will emerge from continued observation, careful analysis, and honest interpretation. The process may take years. The answers may surprise us, but the journey of discovery is worth taking. Sleep well, knowing that somewhere out there, 3i Atlas is still moving, still carrying its secrets, still waiting to reveal what it truly is. Good night.